algebra lesson is going to focus on graphing polynomial functions. So we have a few steps that we can take in order to graph a polynomial function. First, we're going to use the leading term test to determine the end behavior. And that comes directly from lesson 4.1. Then we're going to find the zeros of the function by solving. Any real zeros are the first coordinates of the X-intercept. So we could use the quadratic formula. You could use factoring. You could use completing the square. Or even the square root property that we learned back in Unit 3. We're going to use those x-intercepts in order to divide the x-axis into intervals and choosing a test point to determine if we're going to be above or below the x-axis. We're also going to find the y-intercepts. So we want to find where our values cross the y-axis. If necessary, we may need to find additional points so that we can get the general idea of what our shape will look like. And as a partial check, we can use the facts that the graph has at most a certain amount of x-intercepts and at most amount of turns. Multiplicity of zeros can also be considered in order when checking where the graph crosses or is tangent to the x-axis. We can also check the graph with a graphing calculator. Let's look at the graph of negative 2x to the fourth plus 3x cubed. It's already written in descending order. So we can look at the leading term test to determine which way our front and our back of our function will look like. Is they going to be going up? Are they going to be going down? One up, one down, and in which order that it might lead. When I'm looking at negative 2x to the fourth, we have an even degree and a negative coefficient. This tells me then that using our leading term test, that both ends are going to go down. We're unsure what's going to happen in between, but we're going to discover what that might be. Also, we're going to have at most 4 real zeros because our power is 4. So we're going to have at most 4 real zeros that we may or may not be looking for. Now I can solve, and in this case I'm going to factor because I only have 2 terms, and I see that those terms do have a common factor of negative x cubed. When I take away negative x cubed or divide out negative x cubed, I'm left with negative x cubed equal to 0 and 2x minus 3 equals to 0. When I solve the left-hand side, I'll divide by negative 1, which is still 0, and take the cube root of 0, which is still 0. Or our result could be add 3 and divide by 2. So right now I'm going to plot those 2 points because those are my x-intercepts. And I know that on the far left my graph is going down, and on the far right my graph is going down. We've now divided our graph into 3 sections. What happens from negative infinity to 0, from 0 to 3 halves, and then from 3 halves to infinity? Are our values positive? Are our values negative? Are we above, below, or on the x-axis? Let's go to the next page and determine. So we had our intervals here. From negative infinity to 0, from 0 to 3 halves, and from 3 halves to 2. We need a test value in each one of those, and it could be any test value in those intervals so that we can determine if the sign is positive or negative. I'm going to choose a nice easy value. So when I plug in negative 1 back into our original equation, so when I plug negative 1, I take h of negative 1, I end up with a negative 5. The part that I'm looking for is the negative part. My value is negative, so I'm going to be below the x-axis. When I take h of 1, a value that's in between 0 and 1.5, I get positive 1. I'm a positive, so I'm going to be above the x-axis between 0 and 3/2. Between 1.5 and infinity, a good number would be 2. So when I take h of 2 and evaluate, I end up with a negative value. So I know that I'm below the x-axis. We've also found 3 points that are actually on our graph itself. -1, -5, 1, 1, and 2, -8. If I were to go back to the previous screen and kind of fill the rest of this in here, we determined that we were negative on the interval between -infinity to 0. So we were negative here, positive in this interval, and negative here. So I know that my graph at this point is going to look something like, hit this point, we're going to go positive, and then we're going to go back to negative somehow. Some such derivative thereof is what it's going to about look like. Let's actually see what it's going to look like by filling in more points. We now need to determine the y-intercept. We now need to determine the y-intercept. So to do that, I'm going to plug in 0 for my value, my function value, and evaluate. When I evaluate, I also get 0, 0. So now I have another point. So far I have the points -1, -5, 0, 0, 1, 1, and 2, -8. We also have the points at which we have our, on our graph itself, that gives us whether we're going to have a positive or negative value. We can find additional function values to finish off our graph to see more specifically. And we can also follow up using Desmos to help verify that what we're finding algebraically is actually what's happening to the graph itself, as a way to double check our work. All right, graph the polynomial function 2x cubed plus x squared minus 8x minus 4. We're first going to use the leading term test. It's already written in descending order for us. So I have 2x cubed. Our leading term, its exponent is 3, which is odd, and our coefficient is bigger than 1. So I know on the left-hand side, I'm going to go down, but on the right-hand side, I'm going to go up. But I do not know what's going to happen in between. Let's find the zeros. Here I have 4 terms, so my best bet is to factor. And I'm going to factor by grouping. I'm going to take the first 2 terms and the second 2 terms. The first 2 terms, I see that they're both divisible by x squared. When I factor out x squared, I'm left with 2x plus 1. And in my second set, I see they're both divisible by -4. So that I also get the exact same binomial of 2x plus 1. We need to have the exact same binomial so that we can factor out the common binomial of 2x plus 1, which means that I'm left with x squared minus 4. I can factor again. I can factor x squared minus 4 using the difference of perfect squares. The difference of perfect squares provides me with x plus 2 and x minus 2. Notice that our power is 3, and we ended up with 3 different factors so that we have 3 real number solutions. We'll set each factored piece equal to 0. 2x plus 1 is 0, x plus 2 is 0, and x minus 2 is 0. So we have now 3 values of x. X is -1/2 when I subtract 1 and divide by 2. X is -2. And x is +2. Let's see what this might look like when we draw a little sketch of our graph. We're going to jump and skip this page because I'm just going to redo it here at the top of this one. All right. Just drawing a quick sketch of our graph here of our x-intercepts. We have -2, -0.5, and we have +2. That gives us 4 intervals. We have the interval from -infinity to -2. Is this area going to be positive or negative? From -2 to -0.5, is this area going to be positive or negative? From -0.5 to 2, positive or negative? And then from 2 to positive infinity, is it going to be positive or negative? We need to choose values within each of those for a test value. When I use my function, -3 is in between -infinity to -2. So when I plug in f of -3, I get -25. That's key. Our sign is negative, so we're going to be below the axis. So here is negative. I'm going to hit -2 and something might happen. I might stay below the x-axis, or I might now go above the x-axis. I'm going to plug in f of -1 since -1 is between -2 and -0.5. When that happens, I end up with +3. I have a positive, so now I know when I hit -2, I'm now going to be above the x-axis. Between -0.5 and +2, a nice whole number is +1. So when I take f of +1, I end up with a negative value. So now I'm dropping back below the x-axis. And finally, between 2 and infinity, +3 is a nice one. F of 3 gives me 35, a positive value, so I will be above the x-axis. So we're kind of going above, below, kind of alternating. We do have 4 points that we could put onto our graph now. We've got -3, -25, we have -1, 3, 1, -9, and 3, 35, so we can start building the graph itself. We have our values on the graph as I start to sketch it here. We have our x-intercepts of -2, 0, -0.5, 0, 2, 0. I've put on here the -3, -25 would be super far down here somewhere. But I have -1, +3, we have 1, -9, and then 335 would be like way up here. So we're not going to graph those pieces. Let's find the y-intercept to see what might happen at the y-intercept. So to find the y-intercept, we plug in 0 and evaluate. This ends up being 0, 0, 0, so -4. We also now have the point of 0, -4. We knew the left side was on below, in the middle between -2 and half. -0.5 is above. From -0.5 to 2, we knew we were below, and then from 2 to infinity, we were above the line. We can find additional values to continue. It's okay to just draw a sketch of what your graph might look like to verify, and then of course, again, using decimals to verify. Let's try one more, or a couple more examples just to verify that we understand where we're at. I have x to the 4th minus 7x cubed plus 12x squared plus 4x minus 16. That's telling me, and it's putting it in factored form for me, that we have x plus 1, x minus 2 squared, and x minus 4 is its factored form. Looking at the leading term, I have x to the 4th. I have an even degree and a coefficient that's greater than 1. So I know that both ends are going to go up. Since it's already been factored for us, we can set each factored piece equal to 0. X plus 1 is 0, x minus 2 squared is 0, and x minus 4 is 0. When I solve them then, I'll have x is equal to -1, 2, and 4. So I know on the right-hand side we're going to be going up, and on the left-hand side we're going up, but what's going to happen in between each one of those intervals? We had the intervals from negative infinity to -1, -1 to 2, 2 to 4, and then 4 to infinity. Using our test values, I'm going to plug in g of -1.25, which you certainly could do a whole number, but just showing you that you could use any value. I end up with, it doesn't matter what value you use because we just want to know what is the sign. Is it above or below? I end up with a positive, so I'm going to be above the line from negative infinity to -1. When I plug in g of 1, I end up with a negative value, so I will be below. From 2 to 4, when I evaluate at 3, I end up with a negative value, so I'm staying below. So at this point here between 2 and 2, I must just come up and hit the top of the graph, but because I'm staying below that line, below that x-axis. And finally, g of 4 1/4 is also a positive, so now I'm going back above the line. Let's find our y-intercept. When I substitute 0 in for my x value, so 0, 0, 0, 0, -16. So 0, -16 is my y-intercept. Here are my x-intercepts. So again, notice we were below the line between -1 and 2, but we stay below, so we must just come up and touch this line here. This is directly related because we had that value x minus 2 squared. It is because of this square that we only dip and touch the x-axis. We don't actually cross the x-axis because it's an even portion or an even exponent. And we'll talk more about that later. Now let's talk about the intermediate value theorem. The intermediate value theorem says that if we have a polynomial function and it has real coefficients, if I were to plug in two different values and substitute them and they have opposite signs, then we know that it must dip through the x-axis. If we plug in two values and they have the same sign, they're on the same side of the x-axis. So notice here when I have this random function given, and when I substituted 1 in, I ended up with a positive 5. But when I substituted 3 in, I end up with a negative value. Therefore, somewhere between x is 1 and x is 3, there must be a 0 in between because we go from a positive result to a negative result. It doesn't tell us what the value is. It just tells us that somewhere in between there is a 0 that lies between there. It could be a decimal, so don't assume because the whole number is between 1 and 3 is 2 that it's going to be there. In this case, it is. However, don't always assume that. Use the intermediate value theorem to determine whether x cubed plus x squared minus 6x has a real 0 between -4 and 2. So I want to know on my x-axis here, if between -4 and -2, is there a 0? Does our graph cross the x-axis in between there? So I'm going to substitute -4 into the equation for both of them and determine if their sign is positive or negative. Here we'll end up with -4 cubed, which is -64, plus 16, plus 24, a negative value. So when I plug in -4, I have a negative value. You could determine what that negative value is, of course. When I substitute -2, I'll have -8 plus 4 plus 12, a positive value. When I plugged in -2, I ended up with a positive value. So in order to get from here to here, we must cross the x-axis somewhere. So because they have opposite signs, it does have a 0 between -4 and -2. I don't know what that 0 is. It just tells me that there should be a 0 in between there. Let's try part B here. We have x cubed plus x squared minus 6x, the exact same one. But is there a 0 between -1 and 3? Do we cross the x-axis? So let's substitute our values in. Let's start with -1. -1 cubed is -1, plus 1 plus 6 is a positive value. When I substituted in -1, I ended up with a positive value. Let's substitute 3. 3 cubed is 27, plus 9, minus 18. Still not enough. We're still going to be positive, regardless of what the number is. So these are two, it's not going to be a nice straight line, obviously. It could do a loopy-loo of some kind. But notice that we're staying positive. We're not dipping below the x-axis. So because they have the same sign, it is not possible to determine whether there is a 0 between -1 and 3. A couple more examples with the intermediate value theorem. Here we have a few fractions. We want to know, is there a real 0 between -half and half of 1/3 x to the 4th minus x cubed? So here's -half and +half. Let's substitute -half in first. Here we'll have 1/3 times -half to the 4th. That's the same as 1/3 times 1/16. So -half times -half times -half times -half. -half cubed would be -1/8. However, when I have a negative and negative, we turn into a positive 1/8. It doesn't matter what these values are, they're all positive, so I know I'm going to end up with a positive value. So when I plugged in -half, I have a positive value. Let's try +half. This time I'll have 1/3 times 1/16. However, when I take +half cubed, I'll end up with positive 1/8, but I have the negative there, so -1/8. This is equal to then 1/48 when I multiply across minus 1/8. Well, 1/48 is much smaller than 1/8, so if I subtract a larger number from a smaller number, we're going to end up with a negative. So here we have a negative. They have opposite signs. So somewhere it does have a 0 between -half and half. Again, we don't know what that is, but we do have a 0 between there. Let's use the same function and determine if it has a 0 between 1 and 2. Let's start by substituting 1. 1 to the 4th is 1. That will then give me 1/3 minus 1, which would be a negative value. Now let's try 2. So here we have a negative value. Let's try 2. 2 to the 4th is 16, and we have 16/3 minus 8. Oh dear, another negative value since 8 is bigger than 16/3. Here, because they have the same sign, we're not able to determine if there is a 0 between 1 and 2. And this concludes our lesson on graphing polynomial functions and then using the intermediate value theorem.